Now that we have defined what subgame is, now let's define an important concept called subgame perfect equilibrium. So this is a subgame perfect equilibrium are actually a subset of Nash equilibrium of an extensive form game. So if we have, for extensive game, we have a set of Nash equilibriums, subgame perfect equilibrium will be a subset of this set. And we define it as like this: a Nash equilibrium is called a subgame perfect equilibrium, or in shorthand SPE, or sometimes it's also written as SPNE, subgame perfect Nash equilibrium, if and only if it is a Nash equilibrium for all possible subgames of G. This means that if we find a Nash equilibrium, and for every possible subgames that we can consider, we see that indeed that Nash equilibrium is Nash equilibrium for all possible subgames, then we say that that Nash equilibrium is a subgame perfect Nash equilibrium, or SPE. And from this concept of subgame perfect equilibrium, we can define whether a threat is credible or not. So we say that a threat is non-credible if it is not a subgame perfect Nash equilibrium. So if a given Nash equilibrium is not subgame perfect equilibrium, then we know that that player who is threatening the other player will not be able to maintain his threat when if they end up on that node. For example, let's look into this example again. We saw that there are three Nash equilibriums for this game: BHC, AGCF, AHCF. So we want to find that if they are subgame perfect equilibria or not. For example, the first one, BHCE. So BHCE. We immediately see that this is not a subgame perfect equilibrium. Why? Because if we consider this subgame, the subgame starting from node H4, if you denote this H1, H2, H3, H4, this subgame where there is only one player, the action profile BHCE is not a Nash equilibrium, because here we see that player 1 is playing H and getting a utility of 1, but he can easily change his decision from H to G to get a utility of 2. So he can profitably deviate from his decision. So this is not a subgame perfect Nash equilibria. What about AGCF? So let me erase this. Okay, so AGCF. So A, G, C, and F. So is this a subgame perfect Nash equilibrium? Well, we have to check all of the subgames. For example, in this subgame starting from node H4, this is indeed a Nash equilibrium, because if player 1 decides to change his action from G to H, he will get his utility will decrease from 2 to 1. So for this subgame, this is the Nash equilibrium. What about for this subgame starting from H3? For this, we also see that this is a Nash equilibrium. Why? Because if player 2 changes his decision from F to E, then instead of getting 10 units of utility, here in this subgame, the outcome will be F, G, and so this will be the outcome. So player 2 will be getting 10, but if player 2 decides to change his action, then he will get 5 units of energy, so 5 units of utility, so his utility will decrease. What about player 1? Well, as we have seen before, the player 1 has no incentive because his utility will decrease from 2 to 1. So this AGCF is a Nash equilibrium for this subgame. And what about this subgame? Well, we also see this is a subgame for only player where there is only player 2. And if in this case player 2 is getting 8 for this action profile, player 2 is getting 8 units of utility. If player 2 decides to change his action from C to D, he will get 3 units of utility. So his utility will decrease. So this is also not profitable. So we saw that this action profile is actually Nash equilibrium for all possible subgames. So this is indeed a subgame perfect Nash equilibrium. So let's now look into the third case, which is AHCF. So AHCF. So this will be the outcome. Now again we can see that this is actually not a subgame perfect Nash equilibrium, because in this case player 1 in this subgame, player 1 can actually change his decision to increase his utility. So this is not subgame perfect Nash equilibrium.